The last part of our first law of thermodynamics content is just our definition of work here. So work is energy transferred by applying force across a displacement from physics. There are a lot of different types of forces in physics, and each type of force has a corresponding type of work. The easiest way to define this is in terms of the differential work, d bar w. So again, physics tells us, work is something that's sort of easy to define and measure. We'll find that in thermodynamics here as well. So mechanical work has a subscript m for mechanical, so W sub m. If we define it in terms of the differential work, we find the differential work, d bar work mechanical, is negative P external times dV. So P external is the external applied pressure. dV is the differential change in volume. Again, to understand what we're talking about here with the d bar work mechanical is this sort of graph we can think about. Let's say we have an initial point up here. The external pressure is changing in some way throughout this process. The idea is that if I take some specific little time here, maybe this little slice right here, right at this initial time, there's an initial external pressure. There's a very small little initial dV. Again, I guess we've got this one as well here to look at. So an initial external pressure, an initial little change in volume, that adds up to a little bit of work, d bar w. Then again, to get an overall work, what I do is I integrate these little d bar w all across my process from initial to final. So integrating from initial to final, I get on the left-hand side, the integral of d bar work is just the mechanical work during that overall process from initial to final. And I just then have to integrate on the right-hand side, integrate from initial to final, the external applied pressure with respect to the volume. So this whole area under the curve is the amount of mechanical work that I have. It has this negative sign in front of it in the definition. That's important so that the sign on the work matches what we want. We, in our class, are going to always define work such that if I have a positive work, that's energy, that's work done on my system. If I have a negative work, that's work done by my system. Again, bar tells us this is not a real thermodynamic variable, only defined over this path. So that's why, again, when I integrate from initial to final here, I just get the mechanical work, whereas if I integrate dV, dV over here, if I integrate that, again, I can't necessarily do that here because I don't know that it's constant, but if later I integrate dV on its own, since V is a real thermodynamic variable, volume only depends on the current state, this thing I can integrate as a normal integral, say it's Vf minus Vi, which is equal to delta V. The change in volume doesn't depend on the path. Volume, again, just depends on initial and final, which is very different from work, which does depend on the exact path from initial to final. Okay. One other key type of work. Mechanical work is really important because anytime we do a process in chemistry, there's always the possibility of the volume changing a little bit. When we produce gases or consume gases, there's large changes in volume, but even any process where we change temperature, change the properties of our system, we have slight changes in volume that we might need to worry about. So mechanical work we always have to worry about, even if we're not thinking that we need to. Anytime there's potentially a volume change, increase the temperature, the volume increases a little bit, we have to worry about how much mechanical work was done on or by our system. Another common type that we'll look at a lot is electrical work. That's a nice way to view basically a type of work where we're sort of intentionally doing something, right? Getting some energy out in a battery or something like that. In this case, the electrical work, I'm using subscript E here for electrical. And again, d bar work electrical is the differential electrical work. These variables, unfortunately, we've used in other places for V for electric potential or voltage. So I'm subscripting with an E here to distinguish it from volume. So VE is our electric potential in volts. dQ, E is the differential electric charge. There it is. then the electrical resistance over here in ohms, electrical current in amps. At the end here, d bar Q electrical is I times dt. For resistor, VE is I times RE. So this is our final picture here again. This definition will work, but more commonly we want to do this in terms of current. So in terms of current, we have the voltage is I times the resistance, and d bar work electrical. If we plug in for the voltage there, we get I squared R times dt. Into our electrical work in general, we integrate from an initial time to a final time. I squared times RE times dt. Again, we can interpret that as the area under this graph. I measure current versus time. And then I can see here, okay, here's the little amount of electrical work that's done. Add up all those little pieces of electrical work to get the overall electrical work during a given process.